Today we're learning lesson 11.6, area of regular polygons. Now this is one of the tougher lessons on area, so be sure to pay special attention as these are broken down. Reminder, so regular polygons have what, right? Regular polygons was a word for something being both equiangular and equilateral, or in other words, all sides are congruent, all angles are congruent to each other inside a regular polygon. So same here, these are all marked twice, just to avoid any confusion that these are equal to these, right? Just specifically this pentagon has all 5 sides congruent, all 5 angles congruent. Important parts of regular polygons. Now, looking at the picture here, you're going to kind of tell that we're going to use some terms similar to a circle, but we're also going to use specifically these triangles that we can turn from any regular polygon. We can turn it into a number of triangles in order to solve. So, center of the polygon is the same as the center of its circumscribed circle. Now, circumscribed, circum comes from around, the word around in Latin, but drawn around, the circle that is drawn around, and the points are just touching on it, right? The radius is, again, the radius of the circle. So that is typically, though, here, from the center to the vertexes, right? Center to vertex, those are all radiuses that we normally think of specifically for circle, but in this case of the regular polygon. Apothem. Now this is PQ here, is the apothem. And PQ is the distance from P perpendicular to the midpoint of MN, right? So distance from the center to any side of the polygon. This is the height to the base of an isosceles triangle that has 2 radii as legs, which makes it sound confusing. But in this picture, PM and PN are radii, so this is the isosceles triangle, triangle PMN, where angle M and N are the bases, and PQ would be the height of that triangle. Now, central angle is the angle formed by 2 radii drawn to consecutive vertices of the polygon. To find this, what we're going to do is take 360 divided by n. Well, what's n? N is the number of sides. So what they're talking about here is this angle right here between 2 radii, right? Line to this vertex, line to this vertex. So this would be a plural line to both vertices, and the angle between them would be our central angle, as it says down here in green. Now, that angle is not going to be that useful to us. However, we are going to use an angle that is 360 divided by 2n, and you'll see why that is in a little bit here. Now, as you could tell from that last picture, they have broken down the I believe it was a pentagon, maybe the hexagon, sorry, hexagon, into a triangle. And this hexagon has how many triangles on the inside when we break it into that? 1, 2, 3, 4, 5, 6, right? If I numbered them all, we have 6. Matches the number of sides. Now that's how we're going to be finding area, and more importantly, using that central angle, right? I'll discuss why we need 360 divided by 2n. So here, the important triangle for us, I just talked about this being the kind of triangle we were looking at. However, the triangle that's most useful for us here, let me see if I can highlight it, is this triangle right here, from the vertex down to the base, giving us a right triangle and back up. And why that is because we'll have it, one side is the apothem, one side is the radius. Now this is very infrequently used. We are most oftenly using apothem and side length. We won't see radii as often, just a heads up there. And right triangle, we can bring back that chapter 7 right triangle trigonometry, which would be SOHCAHTOA, right? So the angle here in red is 360 divided by n, where it's the number of sides. So like in a triangle, as weird as it sounds, we'll break a triangle into 3 triangles, and 360 divided by 3 would be 120. However, when we break it down into this specific triangle we cut this 360 divided by n in half, right? We're basically doubling the number of triangles. So in that case, 360 divided by 2, in the example I just kind of mentioned, was a triangle. So 360 divided by 2 times 3 is divided by 6, gives us 60 degrees. So if this was 120, this angle is exactly half of that, 60. And this is what we'll be using to make this triangle. And given one side length, we can find the other that we need. Right? So if we're given apothem, we can solve for a side. If we're given the side length, right, that would be the whole. Notice this is half side. And why? That's because it's one part, one half of the triangle in this picture, right? It's this part of the triangle. So it's not the whole side MN, it's MQ. And then lastly, right, just to break it down more, this is specifically the triangle we'll typically draw. Given apothem, we'll fill that number in. Given side length, we'll just do the math, divide it by 2 to get this number. And then we always will have this number because they will tell us how many sides. Is it a nonagon? Is it an octagon? Is it a pentagon, hexagon? Some of the numbers, like hexagons, have nice numbers because 360 divided by 12 is 30, and then we'd have a 30, 60, 90 triangle. So those are nice ones. As I mentioned, triangle before, if we divide this by 2 times 3, we get 60 degrees. Triangles give us 60, 30, 90 triangles as well. And I believe one other one gives us 45, 45, 90. I want to say that is a square would give us 45, 45, 90, or a regular quadrilateral, if you want to phrase it that way. So getting on to some basic problems here. Given ABCDE is a regular pentagon inscribed in circle F, find each angle measure. So AFB is what? Right, so we've got 1, 2, 3, 4, 5 sides, and so 360 divided by 5 gives us 72 degrees. Find the measure of angle AFG. Well, this is exactly half of AFB, so we will have 36, but we would do 360 divided by 2 times 5, or 10, giving us 36. So this came from 2 times the number of sides. Lastly, angle GAF. So if this is a right triangle and we have 36 degrees here, 90, this needs to finish us adding up to 180, or even shorter, if we have a right triangle here, these two angles will add equal 90. So 90 minus 36 gives us 54 degrees. Next, identifying some following parts before we get to solving the area for these, we've got center, right? Center is going to be point P. Radius is going to be either PX or PY. Apothem is going to be PQ. Apothem has the perpendicular. Okay. And central angle would be XPY or YPX. I just wrote one of them, and now we're going to find the following angle measures. So XPY is 360, right? If we drew all the triangles around just for a second, you realize that we basically form a circle of triangles, and that's why it's 360 divided by how many triangles we have, 1, 2, 3, 4. So 360 divided by 4 would give us 90 degrees. XPQ is going to be half that angle, so 360 divided by 2 times 4, or 8, gives us 45 degrees. We could have also just taken this 90 if we found it first and divided by 2. So 2 different ways to do that. However, typically we won't need to be finding this 90. So most of the time we'll just go 360 divided by 2 times the number of sides. PXQ is the other angle, right? If we found 45 here, what's this angle? 90 minus 45 leaves us with 45 degrees. And moving to the next part here. Now, area of regular polygons is found by breaking it into triangles, as already stated, and the number of triangles will match the amount of sides it has, right? So, for example, we've got a hexagon here, 1, 2, 3, 4, 5, 6, and we're back to triangle 1, right? So, if we've got 6 triangles, our base is side, our height is apothem, we've got half apothem times side, and we have 6 of them. So half apothem times side times number of sides. And they like to do that as half ANS, because you could also say, if we laid them all out straight, it would be the bottom, right, of all these bases would be N times S is the perimeter. So that's why they break it apart like this. Half AP or half ANF. I will use the ANS for our class. Now, also a little note is some of the common degrees, right? If we had 360 and it's a triangle, 360 divided by 3, you get 120. 360 divided by 4, because we've got 4 sides, would be 90, and so on, 72. 6 sides, 60. Okay. So, starting here, we've got this pentagon, and they give us a lot of information. They're giving us the radius is 8, the apothem is 6.5. What is the side, right? Because we need half ANS in order to solve. And so there's half ANS right there. Usually I do a checklist that, hey, I've got apothem. I know I can count. There's 5 sides, so we've got a number of sides. I just need the side length. and we've got a right triangle right here, so I'm going to draw a little bit bigger. We've got this right triangle, and we're solving for the half s. So 6.5 squared plus half s squared equals 8 squared. Now half s is kind of tricky because then you're actually going to get 1/4 s. So how I like to write it is I like to write it as 6.5 squared plus b squared is 8 squared. Solve for b squared, and then just keep a note that that is half of your side, so we'll multiply our final answer for b by 2. Subtract 6.5 squared from each side. Now we have the setup. In my calculator, I got 21.75. Now, square rooting that would help, but in general, I like to say, well, this is half side, so when I square root it, I got 4.663, and this is half of s, so times 2 to get full s, and 9.33. And now I have all three pieces. I'm going to plug it in for area. Area equals half. Apothem was 6.5. Number of sides is 1, 2, 3, 4, 5, and then 9.33, giving us 151.61 units squared. Now it did say find the perimeter as well, so now that we finally have our sides, 5 times 9.33 will give us the number of sides. Number of sides times side length, right? They're all the same because it's regular. And I get 46.65 units, not units squared. Next, we've got a triangle. Now, most people would think, well, just find the height, find the base, and we're ready to go. It's actually, in this case, still easier to do it the way we're going to do. So we're going to do half a and s, right? And first, we need the angle this time. They only give us one side. We're going to need an angle, and we're going to need to use our trick. So in this case, area equals half a and s. Apothem is 5. I count 3 sides. I'm, again, solving for side. So with this triangle, apothem is 5. This angle 60 degrees. We could use our 30, 60, 90 pattern. This would be s. This would be, this would be x. This would be square root of 3x, and this would be 2x. I chose to use SOHCAHTOA this time just to give you the feel for how that would work, right? If we've got this angle and we've got this side and we're solving for this side, right? Opposite and adjacent. We're solving for opposite, so that is tangent, TOA, right? So tangent of 60 degrees equals b over angle 5, over apothem 5. Cross multiply to get 5 tangent of 60 equals b, and again, reminder, this is half s. So times by 2, we'll get 10 tangent of 60. But 5 tangent of 60 is about 8.660. Multiply it by 2, and I get my side lengths are 17.32. And now I'm set. Area is half. 5 for apothem, 3 sides times 17.32. Ended in a result of 129.90 units squared. Now notice here, I typically round to a second digit, a third decimal out here to keep it accurate. I want this answer before I multiply by 2 to be as accurate as possible, and so that I'm not rounding 3, 4, 5 times in a problem. Because I'm probably going to round here, and now when I plug it in, this might get rounded a second time. The more you round, the further your answer is off from the true answer. So that's why I try to limit it. Next, we need perimeter. Perimeter equals number of sides times sides, and we get 3 times 17.32 with a 51.96 units is our perimeter. Next, no picture. You can draw your own if it makes you feel comfortable. However, mostly we need the triangle. So here we've got, this is what they've given us. Side length is 10. Here's our octagon. Okay, and so we've got angle is 22.5. Where did that come from? 360 divided by 2 times 8, 2n. That's where that is. To get 22.5 degrees, and I've got 5 this time. Why is it 5? I see 10, right? This is half. Technically, this triangle is a zoomed in version of this little picture right here. So not to scale clearly, but just to kind of give you a general picture so you can solve for sides. So again, tangent, because we usually have side, half side, right? Half of 10 is 5, or apothem. One of these two we have, the other one we're solving for. So tangent of 22.5 equals 5 over a. And then multiply, right? Typically these are going to switch spots. 5 over 22.5. 5 over tangent 22.5 would be what a equals, but just to show you that math again, We cross multiply a tangent 22.5 equals 5. Then divide by 22.5 from each side, and that is 12.07. And now plugging that in. Now notice here, I did perimeter early because we already have 8 sides and they're all 10. I could do that right off the bat. I don't have to wait to solve for side this time because I'm solving for apothem. So now I've got apothem. I already had number of sides and sides, so I'm just plugging it in. Half, 12.07 times 8 times 10 gives you 482.84 units squared. Now be aware it would have been pretty easy just to slip in an inches or a foot mark, but I didn't see any, so we're still making sure to write units squared when they're squared and units when it's just simply perimeter. One more example to go, and we've got find the perimeter and area of the regular polygon of a nonagon with side length of 8. Okay, so nonagon, there it is, 9 sides. 9 times 8, 72. We already have our perimeter if you want to go that far. But triangle, this time we've got 20, right? 360 divided by 2 times 9. This is 18, goes into 36 twice with a 0, so we got 20 degrees. And again, tangent, why? Opposite, adjacent. And so tangent of 20 equals 4 over A. We got A times tangent of 20 is 4. To get A is 4 over tangent of 20, which is 10.9899. And so that rounded up to 10.99. And now we're ready to plug it in. Area equals half, 10.99 times 9 times 8 to get 395.64 units squared. And again, all we needed was the apothem there, and there's my perimeter that I did out loud already. So if you haven't noticed, the patterns typically, we need to use trig when we only have either R, A, or S. Now, generally, I like to give you either apothem or side, so that we're using tangent to solve for the remaining piece. We can use special right triangles if it's a 3, 4, or 6-sided polygon, because then we've got the 45, 45, 90, or 30, 60, 90 triangles. And then we use Pythagorean theorem when they give us 2 of them, like we did in that first example. And that wraps up today's lesson. Email me if you have any questions.